Hello and welcome to the iSystem webinar series. Today's episode is about demystifying trace, advanced debugging of embedded software. You will learn about the different trace techniques, about alternatives if your microcontroller does not support trace, and also experience a live demo in winIDEA. My name is Sabrina Kisslinger. I'm the moderator. Today's speaker is Felix Martin, who will lead you through the technical presentation. Felix has been a systems engineer with iSystem for almost 4 years and is an expert in the timing analysis of AUTOSAR-based applications. He helps engineers understand and optimize the runtime behavior of their embedded systems by utilizing techniques such as software and hardware trace. Before we start, I would like to give you some general information. During the webinar, you will be muted. If you have questions, please use the question tab in the menu bar. Below the question tab, the handout tab allows you to download the presentation. Today's episode will be recorded and published on the iSystem YouTube channel. At the end of the webinar, some of your questions will be picked and answered by Felix. All others will be answered by email afterward. And last but not least, please check your audio settings. You may need to adjust your PC audio settings to the source you are using. So in general, the audio settings of this webinar platform need to be the same as set in your local PC. So that's it from my side. Let's hand over to Felix. Over to you.
Hello, my name is Felix Martin, and today we are talking about an incredibly useful but also significantly underutilized debug technique, hardware tracing. By the end of this webinar, you will have a solid understanding of how hardware tracing works and be able to record your first hardware trace in winIDEA. You will also be able to leverage hardware tracing to become a better and more efficient engineer. I will start by explaining what a trace is. We will then discuss how to record a trace and which techniques and interfaces are available to do so. Finally, we will look at 2 demos in winIDEA that show hardware tracing in action. Let us start by getting an understanding of hardware tracing by contrasting it to regular debug techniques. In general, we utilize 2 main techniques to debug, that is to find a problem or undesired behavior in an application, interactive debugging and printf debugging. Interactive debugging is maybe what most developers think of first when they hear debugging. We use breakpoints, stepping, and memory watches to get an idea of what our application is doing. And while this type of debugging is the bread and butter of every software engineer, it has some inherent limitations, especially when dealing with embedded systems. The main issue is that interactive debugging disrupts the real-time behavior of the application. As an alternative to interactive debugging, developers might instrument their application with printf instructions. That means the application generates meaningful messages at points of interest. The messages are then displayed in a terminal so that the developer can understand the application's behavior, what the application was doing. If there is no interface available to transmit the messages, toggling I/O pins can be an alternative to the printf statement. The advantage of printf debugging is that it preserves the real-time behavior of an embedded application. Nevertheless, it is intrusive, and the more instrumentation we add, the stronger the impact on the runtime behavior. The holy grail would be a debug technique that gives us full insight into the execution of the application, like interactive debugging, while preserving the real-time characteristics like printf debugging, ideally without instrumentation. And that is exactly what tracing is. A trace is a list of events with timestamps that represent the behavior of the application. Writes and reads to global variables create a data trace message. That is, a trace event with the address of the variable, the value that was read or written, and of course the timestamp. We call this form of tracing data trace. Instruction create events with the address of the respective instruction. This form of tracing is called program flow or instruction trace. By combining data trace and program flow trace, we can get full insight into the real-time behavior of an application. For example, by visualizing the data as shown here in the winIDEA analyzer. I think we agree that tracing is a powerful debug technique, but the question is, how can we record such a trace? In general, there are two main techniques for tracing: software tracing and hardware tracing. Software tracing is similar to printf debugging in the sense that it relies on software instrumentation. The instrumentation generates trace messages at points of interest and buffers them into memory. From there, the data is sent off chip via an application interface, such as CAN or Ethernet. The advantage of software tracing is that it does not require any special hardware. However, it has limitations with regards to the number of trace objects and the trace duration. Like printf debugging, it is intrusive and creates an overhead for the application. Hardware tracing, on the other hand, relies on a dedicated on-chip trace module to record events. The events are then sent off chip either via the debug interface or via a dedicated trace interface. The beauty of hardware tracing is that it does not generate any overhead and does not disrupt the application. Moreover, it allows for a large number of trace objects and for significantly longer recordings compared to software tracing. Depending on the use case, trace durations of multiple seconds to multiple minutes are feasible. Hardware tracing also enables a couple of advanced use cases, such as debugging the application over a reset, unlimited OS profiling, code coverage analysis, and recording peripheral events, such as interrupts or direct memory accesses. The downside of hardware tracing is that it must be available on the microcontroller in use, and it requires dedicated hardware, such as an iSystem debugger. I want to mention that there's a third category called hybrid tracing. Hybrid tracing is any technique that combines elements from hardware tracing and software tracing. For example, the ARM Coresight System Trace Macrocell, STM, automatically generates data trace messages for writes into a dedicated memory area. Other examples for hybrid techniques would be Renesas RJ50 software trace and PowerPC ownership trace messages, OTM. These hybrid techniques are also called instrumentation trace. Anyway, let's take a look at hardware tracing in more detail. As mentioned on the previous slide, hardware tracing relies on a dedicated on-chip trace module. The on-chip trace module has different submodules for recording program flow, data trace, and instrumentation trace. Depending on the microcontroller architecture, we have more or less freedom in configuring what each of these submodules record. For example, we might want to limit program flow trace to a certain function or only record certain global variables with data tracing. The recorded data is then compressed and packed into a trace message. Depending on the trace interface, the message is sent off chip or stored into a buffer and read out by the debugger. Eventually, the data will arrive at the host PC where a debug tool such as winIDEA processes it for analysis by the user. It is important to understand that the on-chip trace module uses compression to allow recording for meaningful periods of time, especially for program flow trace. Usually that means that only program counter values that create a non-sequential flow of the program counter, such as jumps and exceptions, create a trace message. The debug tool then reconstruct the full instruction sequence on the host computer. Lastly, timestamps are added to the trace either on chip or by the debugger, depending on the trace module and interface. To get the trace data from the microcontroller, there are two techniques. The first one works via the regular debug interface. The on-chip trace device stores the trace messages into a dedicated on-chip trace buffer from where the debugger reads them via regular debug port, such as JTAG or DEB. The second and more powerful technique utilizes a special trace port. A trace port is a dedicated serial or parallel interface over which the on-chip trace system can send out trace events directly to the debugger. In general, a dedicated trace port provides much higher data rates at the expense of a higher pin count. If you want to utilize trace, the first step is to figure out whether your microcontroller has trace capabilities available. Depending on the microcontroller vendor and family, that information may not be readily available, so feel free to reach out to iSystem to ask about your device. For the Infineon Oryx microcontroller family, a so-called MCDS, or at least a mini MCDS, is required to record trace data. The upper part of the block diagram shows the regular part of an Oryx microcontroller, including the on-chip debug system and the debug port. The lower part shows the multi-core debug system, MCDS. That is how Infineon calls their trace device. You can recognize the building blocks we discussed earlier. POBs, processor observation blocks, and BOBs, bus observation blocks, have access to the CPU cores, the main system bus, and peripherals to record program flow trace, data trace, and more. Interestingly, the Oryx provides both a debug port and a trace port. If the user utilizes the debug port for tracing, the MCDS buffers the trace messages into the emulation memory, from where the debugger reads the data via the device access port. For higher performance, you can use the HGBT trace interface, over which the MCDS can stream out the data directly. As we would expect, the trace port provides a significantly higher data rate compared to the debug port. By now, you're probably all hyped up about hardware tracing and want to utilize it at your current project immediately. Eagerly, you consult the user manual of your microcontroller to read about its trace capabilities, only to find out that it doesn't have any. Or worse, it has trace available, but the trace port is not accessible on your PCB. Sad day. But oh wait, there might be a solution. Emulation adapters exist for many microcontroller families. To use an emulation adapter, you replace the microcontroller on your PCB with a soldering unit. You then attach the adapter to the soldering unit, in this example via the nozzle on the left side. The emulation adapter features a bigger derivative of the microcontroller that includes a trace unit. The adapter also provides a debug and a trace port depending on the microcontroller family. So in other words, you can run your application as usually while recording trace data in a non-intrusive way. Different emulation adapters, such as the one on the picture for first generation Oryx microcontrollers and for many other families, including second generation TC3XX Oryx devices, are available from iSystem and other vendors. Alright, enough theory. Now it is time to record our first trace. In this first example, I want to demonstrate how to record an OS-aware trace. OS, together with RTE profiling, provides detailed insights into the timing behavior of tasks, ISRs, and runnables. This is helpful for debugging timing-related issues, but may also be mandatory to fulfill requirements that demand quantified data about the CPU utilization of an application. The sample application uses the ETAS RTE operating system and runs on an NXP S32K148 microcontroller. The S32K148 features a Cortex M4 core and is mounted to an iSystem evaluation board. The evaluation board has a 20-pin Cortex debug and ETM connector available. That makes the 4-pin parallel trace interface accessible by the debugger. Also, we will utilize the parallel trace interface for this demo. Note that tracing would still be feasible without the ETM connector by using the so-called single wire output trace, SWO, that is part of the ARM Cortex-M core site IP and is implemented by the S32K148. Time to start winIDEA. For OS profiling, we add a so-called ORT file to the workspace. The long and the short of the ORT file is that it points us to two global variables, running task and running ISR, that we can record via data tracing to see the, you guessed it, tasks and ISRs. After downloading, we open the winIDEA analyzer and create a new trace configuration. We select Automatic and click OK to get to the Analyzer configuration menu. Note that there are three tabs: Hardware, Profiler, and Coverage. As I've mentioned before, hardware tracing allows for non-intrusive code coverage analysis, but that's for another webinar. The Hardware tab is for configuring the trace device and the recorder inside the debugger. If we click on Manual Trigger Recorder Configuration, we get full access to the trace device, including the comparators for selecting the resources we want to record. The Profiler tab, on the other hand, allows us to specify how to interpret and visualize the raw trace data that comes from the target. Luckily, in many cases we can specify what we want to see in the profiler, and winIDEA figures out the necessary hardware configuration for us. So let's do that. In this first example, I want to demo data tracing and OS profiling, which relies on data tracing. So we unselect code, which uses program flow trace, and select OS objects. As mentioned before, we care about tasks and ISRs. Just for fun, we also add a variable. To do so, I first activate data areas and then select my variable of interest, iCounter, and add it to the data areas section. And that's it. We click OK and start our first recording. And sure enough, after a few moments, the profiler timeline gets populated with tasks, ISRs, and our counter variable. The green area shows that an object is idle, while the red area shows that a task or ISR is active. Blue indicates that more is going on and that we need to zoom in to see what's happening in more detail. Also note that our counter is incrementing as we would expect it to do. Also note that compared to data acquisition or sampling, where we read out the data value of the counter periodically via the debugger, tracing really gives us every change, every write access to the variable. In contrast to that, if we did sampling, we might observe jumps in the value of the debugger depending on how high the sampling rate is. There are also alternative views to the timeline. The trace view shows us the already decoded trace messages that came from the target. And the statistics view gives us information about the CPU utilization caused by certain OS objects, among many other statistics and metrics. For further information about OS profiling, I recommend our other webinars on the iSystem YouTube channel. And that's that for this demo. Pretty cool stuff. Onward to our last example for today. The second example shows the real magic of trace. It is based on a vector microsur application that runs on a TC399XE Infineon Oryx microcontroller on an ICE system evaluation board. It is from my colleague Armin, who explains the underlying configuration in much more detail in his Oryx webinar that iSystem did in collaboration with Infineon. I definitely recommend that you check it out. Debugging an embedded system becomes especially challenging if we don't have the context of what the application was doing before an error. That might happen when the stack gets corrupted, or like in this example, if we get an application reset for unknown reasons. As you can see, our application runs fine, but we suspect that resets occur sporadically. To confirm our hypothesis, we set a breakpoint at the start symbol. And sure enough, after a couple of moments, the application stops at the reset vector address. To find out why the reset occurs, we consult the call stack, but naturally, after a reset, it is empty. We can find out the reason for the reset itself in the respective registers of the reset control unit, but in this case, we already suspect an application reset, and that is all what the RCU is going to tell us. So there is no straightforward way to find the root cause of the issue using interactive debugging, but we can try to use tracing. On the Oryx, we can employ a technique referred to as post-mortem debugging. That means we tell the trace device to record into the emulation memory in a round-robin fashion. Only when the application hits a predefined trigger, the recording stops and the debugger reads out the data. It is even possible to make the configuration so that we keep data before and after the specified event. Again, if you want to see the configuration in more detail, I recommend my colleague Armin's webinar. Here I have already pre-configured a trace and will not explain the configuration. When we start the trace with this configuration, winIDEA indicates that the trace device is active via the waiting state in the lower right corner of the analyzer. Once the trigger occurs, winIDEA will read out the recording and display the results. Once that has happened, the red cursor indicates the trigger point. The part on the left of the cursor shows what happened before the reset, and the part on the right shows the behavior after the reset. The 8 millisecond gap after the reset is when the boot code of the Oryx runs. By default, the profiler sorts the code and task objects in alphabetical order. However, there is a useful feature that allows us to sort the objects by entry or exit times relative to the position of the black cursor. So if we set the cursor on the reset point and sort the functions by the entry times, we can see the behavior after the reset. In our case, we are interested in what happened before the reset, so we sort the objects by function exits by clicking on the history area a second time. That allows us to look back in time. It looks like the last running task was the user task cost 0 5 milliseconds, and within that task, the runnable cost 0 5 milliseconds. You can see that the terminate task function is also active, which is probably because it has not finished execution before the reset. By placing the cursor at the end of the runnable, we can see the instructions that have been executed in the trace window on the right. The profiler timeline and the trace events are kept in sync based on the position of the cursor. And as we can see, apparently the application itself asserts and reset, kind of what we expected. By going back in time a little bit further, we can see that the reset occurs either when a certain signal is set to 1 or when a CAN message with a specific payload arrives. In this case, the latter seems to be the case, which is indicated by the CAN receive signal function that ran before the runnable. I hope this shows you how trace can help us to debug an issue that would otherwise have been very challenging and tricky to find the root cause for. And that's it for today. I hope you got a good intuition for what trace is about. Do not hesitate to contact iSystem if you have any questions. Also check out the other videos on the iSystem YouTube channel where we go in more detail about tracing and OS profiling. Thanks for your time and attention. And with that, I hand it back to my colleague and we can answer your questions.
Thank you, Felix, for your very precise and to the point demonstration. It is really very interesting how powerful this trace is. Felix, the first one is more for the tool configuration. Does it matter whether I use an IC5000 or IC5700 for tracing?
Yeah, that's a good question. So we saw that there are two main techniques to record the data, right? You can use a debug port or a trace port. So if you use the debug port and you just read out the data from the on-chip memory, then you could argue it doesn't really matter, right? The debugger just reads out the data. But actually, that's not completely correct because there is a technique called upload while sampling where, and that's especially for the Oryx, where you trace into the emulation memory and then read. So you have multiple tiles in the emulation memory. You configure the Oryx to write into them. And while the trace device is writing into the emulation memory, the debugger reads out the data at the same time. And so for that use case, speed matters a lot. And there is a difference in the speed in which the debugger can access the target between the 5000 and the 5700. So for those kind of use cases, it matters. And then also with the 5700, we support the so-called active probes, which also allow faster device accesses and better performance for trace ports. So they have a higher internal buffer, the IC5700. So that means the data that gets streamed out is then buffered inside the debugger. And since that buffer is bigger, you can avoid potential bottlenecks where the trace device creates so much data that that it might overflow the buffer inside the debugger. So I would say there are some use cases where it does not matter, honestly, but there are also some targets where the 5700 will definitely give you a better performance. So like for many cases here with tracing, it really depends on the architecture that you're using, and in doubt you can just ask us, and we will tell you whether you should use the 5000 or the 5700 or whether there's no difference really. But yeah, that's a good question.
So thank you, Felix. This was a really long answer. This was an answer by an engineer, and now you see the difference between my answer and your answer. Thanks that you came in again. Another one, is it possible to use hardware tracing without a debugger?
And no, you always have to use a system, always by O2s. No, just kidding. So yeah, and I mean, in theory, if you have, again, if we think about the two techniques, if you have the emulation memory or the like it's called in the Oryx or the on-chip trace buffer, then you can, of course, if you have a trace device and you have the on-chip trace buffer, then you can configure, for example, in software without a debugger, like with your application, you can configure the trace unit and you can tell it, please trace into the emulation memory, right? That's completely possible. The question is then how do you read out the data? You would need to implement a mechanism to do so. So in theory, you could do trace if you have the on-chip trace buffer without a debugger, but then of course you have to do all the configuration and the data acquisition yourself, and that's of course where the debugger comes in and winIDEA and makes the whole configuration and setup much easier for you. Another example would be the MTB, the micro trace buffer that is implemented on certain Cortex-M devices. That's another example where there's a little trace device, and the MTB, this micro trace buffer, is just a little area, part of the SRAM, and you can trace into that, and also like in a round robin way. And then if like a certain trigger condition hits you, you can access the data. For trace ports, on the other hand, of course, you need a debugger, because there's no on-chip trace buffer, so the data is sent out, and if there's like nobody there to receive it, then you cannot analyze it. So yeah, the tricky question, but yeah, in some cases it's possible to trace without a debugger, but of course, like seriously, it's not recommended. With it's pain, just use a debugger. That's the right way to do it.
And preferably an iSystem debugger, right, Felix?
Exactly.
Okay, another question which comes in is about regarding runnable tracing and profiling. Is it possible to measure the execution time, the net execution time precisely for runnables, not only for tasks and ISRs?
Yes, it's possible. Again, it's a little challenging. So normally, so if you're not familiar with the term runnable is in the AUTOSAR terminology is essentially an object that gets allocated to a task or ISR. So it's like a function, but with defined trigger condition that is then a container for actual computation that the application does. So because a runnable is a function, essentially, program flow trace would be the right way to record runnables. The challenge then, if you use program flow trace for recording runnable, is like as I've showed, like the data creation rate with program flow trace is really high. So you're like interested in a couple of objects, but you really record everything what the application is doing. You get like really high amounts of trace data. So you can use program flow trace for runnables, but you might run into limitations where your trace duration is really short, especially like if you have like an ORX, it might be possible to record the full program flow trace on the ORX for extended periods of time. For example, if you have a HTTP interface, but you will never be able to record runnables for more than one core. And the data will just overflow, even like either the FIFO on the chip, and so you won't be able to record for long periods of time. The other option, how to record runnable, and that's now a little bit tricky. It's no longer pure hardware tracing, but what you can do is use instrumentation, like the AUTOSAR vendors offer instrumentation hooks for the runnables, and you can use those hooks to instrument the runnables very efficiently and with not a lot of impact or like disruptive behavior on the runtime behavior of the application. So that's the second option, instrumentation. That means you trace into a single global variable. So again, not very disruptive. And then by data tracing that single global variable, or if you have software trace or STM trace available, you can then reconstruct the behavior of the runnable. And then the advantage of that is, because, as I said, the runnables don't change as frequently as a full program flow trace, the data generation rate is lower, and then you can record for longer periods of time. So often, unfortunately, if you want to add the runnables into the OS profiling mix, in a little bit of instrumentation is necessary. No.
So let's stick to the runnable and ISR topic. Another question which reached us is it possible to instrument the system to make sure I'm able to see the net time for a runnable, excluding any interruption coming out of another runnable or ISR?
Yeah, so sorry, I forgot about the part with the net execution time. So So let's first go to the program flow case again. If you have the full program flow case, you see all the context switches that have been going on during the recording. So you will also see when the runnable was not active. So in that case, yes, you can see the net execution time of the runnable. If you use instrumentation, as you asked, then it's trickier again. So if you profile the task ISRs and runnables, then you will see when your runnable gets interrupted by other runnables, because that's what you've instrumented. You've instrumented the runnables, and you will see when the runnable is interrupted by category 2 ISRs by the operating system. So you will still be able to get the net execution time. But if you have any ISRs that are not managed by the operating system, like category 1 ISRs, that might just run in the background and are not really visible via data tracing, then you might not be able to get the accurate net execution time. So I would say in general, you are able to get the net execution time of runnables, but if there are hidden interrupts in the background, you won't see that, and then your metrics will be wrong. So it's a good question. You kind of have to know a little bit what your application is doing to get accurate timings.
Thanks, Felix, for that additional explanation. Another one which reached us goes a little bit back into the direction what you had as a first question, the IC 5000, 5700 and overflows you mentioned. So when we get overflows of the trace buffer, does that mean that the data output is messed up, or is the data just overwritten? What does happen then?
Usually the trace device indicates when an overrun happens. So there are like special error trace messages that tell the debugger or whatever device analyzes the raw data from the target that there was an overflow, for example. And in that case, after the overflow, usually that doesn't mean that the trace device just stops recording, just stops recording long enough so that the data is sent out, and then it continues to stream out data in the case of the trace port. So what winIDEA then does is it basically shows you there was an error, and it stops profiling or analyzing the data after the error. So you will never see wrong data in the sense that in the sense that winIDEA will show you like that gap after the error. So to make it short, like when an error occurs, winIDEA like gives you a message so that you are aware that that happened, and also it shows it stops profiling the data after the error, so you cannot accidentally interpret it as correct data. Mm-hmm.
Okay, we still have a lot more questions left and we have some time to go. So Felix, another one is, will my application behave the same when hardware tracing is active?
Yes, it definitely should behave the same, so that, as I said, like during the presentation, the trace devices are able to access the CPU cores and memory buses in a non-intrusive way. That's like what they're built for. That's how the semiconductor vendors design them. Nevertheless, you have additional circuits on the silicon, right? So when you are recording and when the trace device is active, like the heat development on the target itself is different. So, you know, because of that, like in theory, like something on the microcontroller changes. There's additional hardware there, but the trace device itself is designed so that it does not interfere the application at all, as long as it's pure hardware tracing. Of course, if you use one of the hybrid techniques, it's different again. You have some runtime behavior, changes in runtime behavior, but with pure hardware tracing, the answer is no, the application should run the same.
Thanks for that, Felix. And the next one is, how accurate is the timing when I use hardware tracing?
Those are all questions that are very architecture specific. So I had one slide where I showed like there are cases where the microcontroller or the trace device generates the timestamp. There are cases like when you use a trace port where the debugger adds the timestamps. So it depends a little bit on that. So I would say the answer like really depends on the architecture. So you have to take that into consideration. But in general, you can get, I would say, almost cycle accurate timestamps. So you're really like, if your target is running into at 200 megahertz, you are getting 5 nanosecond, or sometimes it's double cycle amount, so 10 nanoseconds timestamp accuracy. It's really that precise for the case where the timestamps are added on the target. For the case where the timestamps are added by the debugger, if you are using a trace port and we assume that the delay that the messages take from the point where they are sent off the trace port and then arrive at the debugger itself, where the debugger then adds the timestamps, if we assume that that delay is constant, which we can assume for some targets, but not for all. So again, it's a little tricky, but for those targets where it is constant, then we actually get the clock accuracy of the debugger itself, which I think is 1 nanosecond. So they are really precise. Definitely, yeah, definitely good enough for all use cases in terms of OS profiling and timing analysis.
Thanks again, Felix. And the next one is about program flow trace. You said that for program flow trace, the trace device creates events that contain only the address of non-sequential instructions. How does the debug tool know which instructions have been executed?
Yeah. So program flow trace is honestly a pretty black magic in itself. I mean, I don't want to claim that I know more about it than I do. Like, we would have to talk to our decoder guys in the R&D department. But in general, as I tried to explain, when you do program flow tracing, it again, if you're running at 200 megahertz and our program counter changes every 5 nanoseconds, it's clear that it is way too much data to just create one message for every PC value. So naturally, the smart hardware engineers have decided to use some form of compression. And so that means, as you said, only non-sequential program counter or opcodes, so only non-sequential instructions like jumps, for example, create trace messages. And the messages contain, as I said, the opcode. I mean, again, and not the opcode, the address. And that's also not fully correct. Probably they don't even contain the address, but like just a small enough subset of the address so that the debugger can figure out the full address. And then what winIDEA has to do is it has to take the addresses, look at the ELF file or into the memory of the application, figure out the actual instruction. And so basically winIDEA has to figure out the instruction itself, and then from that information, with the information from the ELF file, it can reconstruct the program flow, and then gives you the full insight into what the application was doing. And there are some cases, unfortunately very few, but there are some cases where there's where like doing this reconstruction is a little bit problematic. Let's put it this way, because it's so highly compressed. But yeah, in general, the debugger can just gets the addresses of the instructions and then builds everything back together via the information in the download file. That's the process in general.
Okay, thanks again, Felix, for sharing your knowledge with us. And believe it or not, no questions are left, so we're coming to an end for this episode.
Thank you.
Thank you too, Felix, again. And before you leave, I would like to give you some additional information. Don't forget to download the presentation. Check out our free online trace tutorial, our YouTube channel, our application notes. And if you want to, feel free to register for our newsletter to get interesting updates and invites for the Infineon webinar in 2 weeks from now automatically. If questions come to your mind later, feel free to reach out to webinar@isystem.com or your sales or tech representative at iSystem. Thanks for attending, and please fill in the feedback form before you leave, and bye and take care. See you soon.
Bye from my side too. Bye.